Yeah, so I'm Jeff. I work on the Flow team at Facebook. Before we go too much further, how many of you know what Flow is? Just raise your hands. Oh, wow, lots of you. Cool. Okay, so for those who don't know what Flow is a static type checker for JavaScript. It's sort of a linter on steroids. You give it your code, and it tells you if it finds all the bugs in your code, or lots of bugs at least. Now, we started building Flow 2 or 3 years ago when we saw like JavaScript usage exploding at Facebook. People were building, React had just been open sourced, and people were starting to think about React Native, and all these things were blowing up, and it was pretty scary because we had ways of reasoning about our code, the rest of our code, PHP and Java and Objective-C, but we didn't have very many good options for reasoning about JavaScript at Facebook on a holistic level. So it became sort of a thing that we started looking into how to solve that problem, and that's where Flow comes from. Now, since then, Flow has kind of blown up at Facebook. We use it everywhere in a lot of all of our JavaScript code bases has Flow available to them. And a lot of people have found a lot of value out of it, and a lot of people in open source land have also found a lot of value out of it. But it's become clear since then that type checkers in general are kind of a black box to a lot of people. There's not a lot of good insight into how they work. And so this talk is actually going to be about how Flow works internally. It's going to be pretty technical, but I have 30 minutes to go through it. So I'm going to go a little quickly, and I'm going to steal Lynn's idea of suggesting that if I go too quickly, feel free to come back and watch the video later. It's recorded. Okay, so we're going to start basically by showing a simple example here, some source text. JavaScript code that has a typo in it. You notice that we have a variable declaration and then a.lengta. It's contrived code, but it's a type error. Now, the first thing that Flow does with this code is the same thing that any system that deals with source code does, is it parses it. And a parser just takes source text, which is a string, stuff you write, and it generates what we call an AST, syntax tree. And an AST is just a structured representation of the source code that you have. And in this case, we have a list of objects, and each of those objects represents a statement, and those objects have some information about each of those statements. So first stage of Flow, parse the source code into an AST. The next thing we do once we have an AST is this is the first phase of Flow that's pretty interesting. We call this the inference phase of Flow. Now during inference, what we're going to do is we're going to dive into, we're basically going to traverse the AST, roughly depth first, and we're going to extract a bunch of information out of the AST. And this is just us learning about the code before we make some assumptions about it, before we type check it. So on the slide here on the left, we have the part of the AST that we're looking at, and on the right, we have the original source code. I just have both because sometimes the AST can be a little cryptic. And as we go through the infer phase, the first area in memory that Flow deals with is the scope. Now, the scope is probably what you think it is. It's just all the variables that are in the scope at the current spot in the AST that we're traversing through. So the scope is just a table that goes from variable name to variable type. The next area of memory that we're concerned with as we go through the infer phase is what we call the type heap. The type heap is where we store all of the types in Flow, and you have lots of types in your program. And in Flow, each type is represented by a tiny little data structure, just a little object inside of Flow. And you have lots of types, so each object, or each type is represented by one of those little objects, and it sits in the heap. We'll see what that looks like in a second. Okay, so now we've set ourselves up to go ahead and start running through the inference phase. The first thing we're going to look at is we dive into our first statement here, the variable declaration, and we look at the left-hand side of the variable declaration. Now, the AST says that on the left-hand side we have an identifier whose name is A, and so what that means is we're declaring a variable whose name is A, so we're going to create an entry in the scope table, A. And the scope table is a map of variable name to variable type, so we also need to create a type for A as well. Now we create the type over in the type heap, and we create a pointer in our scope map. Don't know what that was. We create a pointer in our type over in our scope table into the type heap so that later if we encounter A, we can sort of trace where the type of A is. Now, the problem that we have right now is that we know we have A, and we know it has a type, but we don't know what the type is. So if we don't know what the type is, how do we create a type for it? The answer to this is we're going to create a type, but we're going to create what we call an open type in Flow. Now, an open type is just a way of saying that we have a placeholder for a type that we're going to figure out later, okay? So because we don't know the type of A yet, we create an open type, and we'll fill it in later. Okay, now the next thing you need to know about Flow is that all types in Flow have a name, like an open type or a number or a string. And all those names end in a capital T. So when we have an open type, we call it an open T. If you look through the Flow source code, you would see open T. And the last thing about types is that they all carry around some data. So in this case, we're going to associate a unique ID to this open T. Remember, open T is a placeholder for the type of A until we figure out what the type of A is. And open T0 is just a unique ID for the type of A. Later, we're going to create more open Ts. That's going to be open T1, open T2. We'll have more. Each one's have a unique ID. Open T0 is A. Okay, so we move on to the right-hand side of the string now. Here we have a string. Sorry, right-hand side of the variable declaration. Here we have a string. And our AST says that we have a string whose value is ABCD. Now, this string doesn't do anything to the scope, so we don't need to change the scope table. But we do need to create a type, another little structure over in our type heap. And this is a string type. Now, string types in Flow are called str_t, capital T, just like I said earlier. And we're also going to store some data with this string type as well. Now, in this case, we actually know the value of the string. Typically, when you talk about type systems, you're talking about just types, not the value. You don't know what the values are. You just know that strings are compatible with strings and not numbers and so on. But because Flow actually knows the value of the string right now, we're going to go ahead and record it. The goal of Flow here is to be as smart as possible as it reasons about your code. And so any amount of information that we can collect and carry around with us, we do. This allows us to track constants through your program, type check things like enums, and so on. So we're going to go ahead and collect the string value as well here and store that with our type. Okay, so now we have created two types for our variable declaration. And the last thing we need to do before we can move on is express how these two types are associated with each other. So let's take a step back. We have a type for A, because A is a variable, and we have a type for a string, because it's a string. And if we look at a variable declaration like this, we see that the string is being assigned to A, so conceptually what's happening is we have the string flowing into A. So this is how we're going to express the relationship between these two types. We're going to create what we call a flow constraint. So that's what this orange arrow here is expressing for us. A flow constraint is just a link between two types, and it says that one type flows into another type. And it makes sense, right? ABCD is flowing into A. Now here's where we start to see Flow differ from the way that a lot of type checkers work. There's a real history to type checking, and it comes mostly from, it has its roots in static languages, things like C and C++. And so because of that, there's sort of a traditional approach to how type checking works. And in that approach, typically what your goal is to be as eager as possible to find out the type of a variable as quickly as you can. So given what we know here, in that approach, what we would do is we'd say, well, there's a string flowing into A, and A is an open T because we didn't know the type, but now we do. There's a string flowing into it, so A must be a string, right? So this is the approach that sort of the traditional type checking algorithms would take. But in Flow, we don't actually take this approach because it turns out in dynamic languages like JavaScript, it's not actually something you want to do. So let's look at a really quick code example to see what I mean. Here on line 1, we have a variable name, just like we did in our other example, and it's assigned Jeff. And if we were to eagerly assume that by assigning a string to the name variable, that name must be a string, then by the time we get to line 4, if this type system assumes, is null safe, then by the time we get to line 4, we've already decided that name is a string, and we're going to give an error if somebody tries to assign null, which is not a string, to name. But it turns out there's not a problem with this code on line 4. There's a problem with this code on line 6, where we assume name is not null. We try to get the first initial off the name. Well, if we were to fix this code, we could do it all entirely on line 6. We could just check to see if name is null, and if it's not null, then we know it is a string. And because of this sort of dynamic nature of JavaScript, there is nothing wrong in terms of bugs. This code will run at runtime, and it will work correctly. But the reason we didn't take that traditional approach to type checking is because even with this fix, with this correct code, eagerly assuming that name is a string would still error on line 4 here. So instead of just replacing OpenT0 with string here, we're going to continue analyzing the rest of our code, and later we'll decide what the type of A is. OK, so we're ready to move on to the next statement. Here we're at a.lengta. This is where we have our typo. And we're going to dive into this syntax tree. First, we look at the left-hand side of the dot, so our object. Well, it's an identifier whose name is A, so we look in our scope table, and we find that A has the type OpenT0. Now we're ready to move on to the property. Property is an identifier of name lengta. Well, if you think about what a property access is, what a member expression is here, it's actually an action. It's like a verb, right? You are extracting a property off of an object. So in order to express an action like that, we are going to create a special kind of type called getPropT. Now getPropT down here is different from the other two types that we created. The other two types that we created were data types. They describe the type of A, which is some data, and a string, which is some data. But getPropT is what we call a use type. Use types describes actions on other types. And use types also have some data associated with them as well. So the property access action has some information about the name of the property that we're accessing. And it also has a nested OpenT inside of it. So we have a little structure, and inside that structure we have another little structure, which is OpenT1. Remember, OpenTs are placeholders for types we don't know yet. And we don't know the type of a.lengta yet. We will figure it out later. So we use an OpenT as a placeholder for that. OK, so again, we've created a new type. And now we're ready to express how it's related to A. So A is flowing into a property access action. That's the way we think about this. So all we need to do here is create a flow constraint between A, which is represented by OpenT0, and the action getPropT. OK? So at this point, we have exhausted our AST. We don't have any more AST to run through. And if you look closely, you'll notice that in the type heap, we now have basically a graph. This is a flow graph. This represents the data flow through our program. And it turns out it represents a lot of information about our program in a way that's pretty different from what a syntax tree represents. So our program starts out with a string. String flows into a variable A, OpenT0. A then flows into an action that's a property access. And we've represented that whole concept in terms of a very well-structured graph. And because we have all that information in the graph, at this point, we're done with our inference phase, and we can throw away source text, and we can throw away scope. And all we need from this point forward is the flow graph. Now, this is the last phase in type checking and flow. This is where we're actually going to find the type error. So the first phase is to create the flow graph, and the second phase is to run through that graph and see if we can find any problems with it. Now, the way that we do that is we run through it one flow constraint at a time, and we start at the bottom. So at the bottom here, we have stir_t flowing to OpenT0. And what we do when we encounter a flow constraint is there's a huge list of rules that are written inside of flow. There's like a big file that just has a bunch of rules for what to do for every kind of constraint that we encounter. So as we go through these constraints one by one, we're just going to look up what to do for that kind of constraint, and then we're going to do it. That's why we call it the evaluation phase. So when we go to that rules table and we look up what do we do whenever a stir_t flows into an OpenT, it turns out the rule there is, it's coded inside of flow, the rule is whenever anything flows into an OpenT, that thing gets forwarded on anywhere the OpenT goes. So here a stir_t is flowing into an OpenT, and the OpenT is flowing into getPropT. So the rule says that stir_t should flow directly to getPropT. Again, let's take a step back and think about what we just did. Let's bring it back to normal life. We, in our original code, had a string flowing into a variable, and then we had a variable flowing into an action. And what we've done in this first step is we've just cut the variable out of that equation. We said we have a string flowing into an action, right? We're going to get a property on a string now. Okay, so this makes sense so far. We have one flow constraint left to evaluate, string flowing into getPropT. So we start at the bottom. We look up in our rules table what's the rule for whenever a stir_t flows to a getPropT. Well, this set of rules is a little more complicated than the last one, so bear with me. I'm going to step through it one at a time. The first thing we're going to do is we're going to create two new types. So in the process of evaluating our rules, we can actually create new types. This is interesting, because it means that our graph is going to expand a little bit. Now, the first of the two types that we're going to create is an instance t, and an instance t just represents an instance of an object. Strings in JavaScript are just instances of string.prototype, so we're effectively desugaring the concept of a string down to an instance of string.prototype. That's what we're doing here. Now, instance t has some data in it. The first is the name of the class that it's an instance of, so string.prototype. The second is a pointer to another type, which is the parent of that class. So the parent class of string.prototype is object.prototype. So we have a pointer up the prototype chain. And the last thing is we have a map of the members of that class. So basically all the things on string.prototype. We've got like 2 lowercase, 2 uppercase, pad left, slice, all these things that are now, luckily, thanks to TC39 on the prototype chain, are in that members map, and it's a map of the name of the thing to the type of the thing. Okay, and the second type that we've created here is a lookup t, and lookup t is very similar to getPropT. In fact, it's almost indistinguishable. It has the same kind of data. It has the name of the property that we're looking up, and it has an open t that represents the result, which we don't know yet. The difference between lookup t and open t is very subtle, and it's just that lookup t looks up the prototype chain. So getPropT pulls a property off of an object. Lookup t looks to see if there is one. If there is, it pulls it. If there's not, it goes up the prototype chain, and then it recurses, right? Repeats. Okay, and the last step we have to do here before we're done evaluating stir_t to getPropT is we have to flow the result of the lookup t to the result of the getPropT. So whatever we find as we look up the prototype chain is the answer for this property, right? So we're going to flow OpenT2 into OpenT1, and we are done with that constraint. Okay, almost done. At this point, we start at the bottom. Instance t flows to lookup t, the rule for that. Step 1, look in the members map. Is the property that we're looking up in the members map? Well, in this case, no, because length to is not anywhere, right? It's a typo. So we don't find it in the members map. The rule says if you don't find it in the members map, find the parent class and flow the parent class into the lookup t. Like that. Now, the parent class of string.prototype is object.prototype. So we're going to create another instance t, except this time it's not string, it's object. And we have a new graph. We start at the bottom. We follow the rules. The rules are, in this case, the same as the rule that we just ran because it's instance t flowing to lookup t again. So is length to in the members map? No, it is not. Find the parent class, flow it to lookup t, and continue on. Now notice that what we've done here, before I explain what mixed t is, notice that what we've done here is exactly the same thing that a VM does, or a JavaScript interpreter would do, like a browser, right? If we look on an object and we don't see a property, then we go up one level until we find the property, and whenever we find it, then we return it. We're doing the same thing here, except we're doing it at a type level instead of a value level. Now, in a VM, what happens when you get to the top of a prototype chain, if you don't find the property that you're looking for, is you return undefined. That sucks, right? You get undefined, and then it floats around your program, and then you get undefined is not a function, and you have no idea what the hell's going on. Well, in Flow, we are a type checker, and that's not useful for us. We don't want to do the same thing. So what we do is we model that the top of the prototype chain is a type that we call mixed type. Now, in type language, mixed type is the super type of all possible types. But in normal person language, mixed t is like a black hole type. Anything can flow into it, but you can never pull anything out of it, right? So in this case, by flowing mixed t into an action of looking up a property, that's an attempt to pull something out of a black hole, which you can't do. So therefore, the rule for mix T flowing into lookup T is create a type error. Now you'll notice that here we have a type error that has a lot of information that we kind of threw away a long time ago. It has the line number, it has like, you have a string and a length, but we gave up string and length a long time ago. Now we're just dealing with mix T and lookup T. There's actually an additional amount of data that gets stored with every kind of type and flow that I didn't show, mostly because there's not very much room on the slides. But we call this data reason data. And basically, every time we create a new type, we stick some data into that type that says why we created that type. Where did it come from? And so as we step through this phase of each step along the way here, we're tracking the reason why we got to where we're at that point in time. So when we get to mix T flowing to lookup T, and we get an error, we have enough breadcrumbs and information to go back and generate a useful error like string. There is no property length to unstring. Okay, so we've seen how we go from source code to type error. Let's pull back a little bit now. That's what we do for a single module. We parse the module, we build the flow graph, and then we evaluate the flow graph to see if there's anything wrong with it. Well, in a real application, you don't just have one module. So this is just an example module, a bunch of types floating around. I don't know what these are, it doesn't matter. But the point here is this is a single module, and in real applications we have multiple modules. So what we're going to do here is we're going to just draw a line around these types to indicate that they're all contained within one module. Right? This flow graph is just for a single module, and our application actually has a second module over here which has its own flow graph. And so what we can do is we can take the process we just ran through and we can do it in parallel. Because these two modules are completely isolated, we can run these two processes in parallel. We can type check two parts of your program at the same time in parallel. This is what flow does when you first start it. When you type flow on the command line, it's going to find all the files in your project. It's going to load them up into a worker pool, and it's going to type check every single one of them in parallel, which actually makes an extremely efficient approach to this process. Now, there is one thing I skipped over here, and it's the fact that in real life, not only do we have multiple modules, but they're usually not separate. Right? They usually have dependencies on each other. They import and they export from each other. So what happens when two modules are next to each other and they're depending on each other? Well, the way that we model an import or an export in flow is it's just a flow of one type from one module into another module. So we have flow constraints that just cross module boundaries. Anytime you see a flow constraint crossing a module boundary, you can be sure it's an import or an export. Well, if these two modules are connected to each other, how do we run them in parallel? Because they're dependent on each other, right? Well, it turns out we've already seen a mechanism that allows us to break these two chunks of the flow graph apart. OpenT. Remember, OpenT represents types that we don't know yet, but we will figure out later. So what we can do is we can take these two modules, these two flow graphs, these two modules, crack them apart, plug in an OpenT at their boundaries, do all the work to analyze them in parallel, and then come back at the end and put them back together. So as we go through in a worker, we will, anytime we encounter an import, we use an OpenT, and at the very end, we connect those OpenTs back to the export that they're importing from. So when you do this one module at a time, next thing you know, you have a huge flow graph, something like this, and it represents your entire application. It's made up of lots of little modules, but it turns out your whole application is connected in a really complicated way. There's flows going everywhere, left and right. So what we do with this flow graph today is we type check it. Right? We run through it mechanically, and we find if there are any type errors. But it turns out there's a lot of really interesting things you can do with flow graphs other than just type checking. For example, if we look at this graph, let's say this graph represents an application that maybe has a form that the user can type like a SQL query or something, I don't know, something dangerous. They can type an SQL query in, and then it's going to go into your application, and it's going to be processed and parsed and executed or whatever. Well, if you talk to a security engineer, he's going to be terrified if you tell him that users are writing SQL queries and submitting them into your application. And the first thing he's going to want to know is, why are you doing that? And the second thing he's going to want to know is, okay, if you have to do it, how can we make sure that you don't have any vulnerabilities in your application? Well, this is something we've done a proof of concept for so far. It's only a prototype in Flow, but it's something that we've sort of proven out, and it's something called taint analysis. What we can do here is if you can indicate where that SQL data is coming into your application, then you can actually trace through your entire application all the places that data is going to go. And next thing you know, you realize you have SQL data coming in from users going to half your application. Probably not what you expected when you wrote the app, but it happens, right? Sometimes you parse and you split the string in two and you send those off to utilities and this happens. So at this point, your security engineer is terrified and he's either going to be super dedicated and sit down and analyze half your application for vulnerabilities, or he's going to tell you to refactor your code so that you don't have SQL queries going around half of it. Okay, moving on to the second thing, the last thing that I think is really interesting that we can do with a flow graph. I think it's actually more interesting than what I just showed. If you look at an application like this, you probably won't notice that in the bottom right-hand corner, you have a bunch of types that are flowing around that don't touch anything but themselves. It's just a tiny little cluster. They're flowing into each other, but they're not flowing into the rest of the application. This means we have types that are associated with code that is not used by the rest of the application. It's dead code. Notice that this dead code spans an entire module, but it also spans parts of other modules. A lot of people recently have been talking about tree shaking, right? This has been sort of all over Twitter. Rollup does a really interesting thing with tree shaking. It can analyze imports and exports coming between modules, and if you don't use a module, then it can omit it from the package that it generates. This is a super granular version of tree shaking. It's not even about imports and exports. We can literally see which properties on objects that you're importing are not used and delete them. So we can take this cycle of code that's not used by the rest of the application, and using a flow graph like this, there's potential to build an extremely optimized version of your code when we minify or we compile it. So yeah, that's what Flow does. It builds the flow graph. It uses the flow graph today to do type checking. In the future, we were pretty excited about going down these different avenues and routes to make it do a lot more things. This is why when we talk about Flow, we talk about it in a sense, not that it's necessarily just a type checker, but it actually really is a platform for code intelligence. And it's specifically that flow graph that gives us a lot of that understanding of your code. We built Flow to use it. We're using it a lot internally. We open sourced it because we think that's the right thing to do, and we're getting lots of reports that people in open source land are finding a lot of value out of it. And yeah, we hope you guys check it out and go give it a shot. Thanks for listening to me.